An isentropic steam turbine processes 2 kg per second of steam at 3 megapascal. So the keyword here is the isentropic process in the steam turbine, which means a reversible adiabatic process where entropy remains constant during the process. And the inlet to the turbine is given. The steam is exhausted at 50 kilopascal and 100 degrees C. So this is the exit from the turbine. 5% of this flow is diverted for feedwater heating at 500 kilopascal. So I see that 5% of the exit comes in this direction for feedwater heating, and the remaining, or 95% of exit, goes in the other direction. Determine the power produced by this turbine in kilowatt. So we are interested in W dot out. I'm going to use the first law of thermodynamics to solve for this problem. First law, in rate form, dE dt equals E dot in minus E dot out. And I'm going to take the turbine as the system. I see that this is an open system, or I can call it a controlled volume. So let's first write down the assumptions in the first law. I'm going to assume that this is a steady flow process. Since there is no change with time, so ddt equals to 0, or the left-hand side of the first law will be 0. So it's going to be E dot in equals E dot out. And I'm going to assume that there is no change in kinetic energy and there is no change in potential energy. Problem says that the process is adiabatic. So there is no heat involved, or heat transfer rate equals 0. And we know that turbine is a work producing device, so W dot input to the turbine is 0 as well. So first law of thermodynamics, E dot in equals E dot out, or sum of M dot in H in equals to W dot out plus sum of M dot out H out. I see there is one inlet to the turbine and there are two exits. So let's call them number 1, number 2, and number 3. So first law will become M dot 1 H1 equals W dot out plus M dot 2 H2 plus M dot 3 H3. We are interested in W dot out, so I'm going to rearrange this equation for W dot out. W dot out equals M dot 1 H1 minus M dot 2 H2 minus M dot 3 H3. And M dot 1 is given in the problem statement, 2 kilogram per second. So I have to determine M dot 2 and M dot 3, and I have to read the numbers for entropies to solve for W dot out. Let's use conservation of mass to determine M dot 2 and M dot 3, or the mass flow rate of steam at the exit. So conservation of mass for a steady flow process in an open system. Sum of M dot in equals to sum of M dot out. M dot out equals 2 kilogram per second. And I see that M dot out is split into two directions. M dot 2 is 5% of M dot out, and M dot 3 is 95% of it. So M dot 2 is 0.1 kilogram per second, and m dot 3 is 1.9 kilogram per second. So m dot 2 is known, 0.1 kilogram per second, and m dot 3 is known, 1.9 kilogram per second. I just need to determine the enthalpies. Input to the turbine, P1 is given 3 megapascal, and the first exit, P2 is given 500 kilopascal, and the second exit, P3 is given 50 kilopascal, T3 is given 100 degrees C. Let's determine its state. T sat at P3 50 kilopascal from table A5 is 81.32 degrees C, which is less than the given temperature, so state 3 is superheated vapor. I can go to table A6 at the given pressure and given temperature. I'm going to read for enthalpy. Enthalpy is 268.2.4 kilojoule per kilogram. So let's take a look at the givens. Problem says that it is an isentropic process, meaning that entropy remains constant. So if entropy remains constant, it means that S1 equals S2 equals S3. I'm going to read for entropy as well. 7.6953 kilojoule per kilogram Kelvin. So let's go back to number 1, the inlet to the turbine. S1 equals to S3 equals to 7.6953 kilojoule per kilogram Kelvin. And the same thing for number 2. S2 equals to S3 equals to 7.6953 kilojoule per kilogram Kelvin. So we just need to determine the states. S1 is greater than Sg at P1, 3 megapascal, meaning that inlet to the turbine is superheated vapor. And S2 is also greater than Sg at 500 kilopascal. We just need to go to table A6, superheated water vapor, and at given pressures and entropies, we can read for enthalpy. H1 is 385 1.2 kilojoule per kilogram, and H2 equals 3206.5 kilojoule per kilogram. So all of the numbers for enthalpies are known. I will go back to the first law of thermodynamics and solve for the only unknown W dot out. It is equal to 2285 kilowatt. And this is the final answer.